Okay, so we're still in the same conversation. What is the main question of organic chemistry? What are the electrons going to do? In order to answer that, we're going to consider two criteria, shape and polarity, or shape and electron density. So 3D bond line structures are going to help us a lot. They're really going to simplify things. They're going to get used to things in our minds, in our eyes, and it's going to really help us. All right, so remember now that all molecules actually take up 3 dimensions, and we're trying to represent a 3-dimensional molecule with a 2D slip of paper or a blackboard or a whiteboard, right? And so consequently, we have to have some conventions that are going to help our eyes see 3 dimensions. Now, the one we're going to use by far and away the most is wedges and dashes, okay? So you're going to have to get your eyes used to this. A wedge, right? That is coming out towards you. And a hash is going back behind the paper. All right? So that's something you're going to have to get your eyes used to. Now recall that with line bond structures, we have a lot of hydrogens on here too, right? So look at this structure. If I've got a carbon here, I'm only showing 3 bonds. There's no formal charge. There must be another bond, right? So it must be that I've got another wedge here and a hydrogen, right? Can you see that? Now it turns out it wouldn't have mattered if I'd have drawn it there or here, right? It still gives us the same basic structure. Now what about over here? Oh look, I've got a wedge, only 3 bonds here. There must be, right, a hydrogen. And you can see that how convenient this is, even with bad art, right? Look at that hash. Well, it's a horrible hash, right? But it doesn't matter. You can tell it's a hash. Does that make sense? So with this structure, super convenient structure, of course you want to be artistic with it as best you can, but you don't want to invest lots of extra time. That's what the whole issue here is, efficiency, right? We want to very quickly and very easily be able to tell what's going on. Now, the textbook that we're using mentions 3 other kinds of notation. There's a Fischer projection formula, which we're not going to use, I think, at all. But you'll see it. Fischer projection formulas, I'm not going to go into how those are structured, okay? But it is a 3-dimensional representation. And we use that for things in biochemistry a lot, for things like, sugars and such, okay? And then there's the Haworth projection, which we also use in biochemistry a lot. Now, these really do... your eyes do get used to these things, but this one I think fits in the eyes better for 3-dimensionality than the Fischer projection, but either way. Now, and this structure doesn't have a name, but we do use this with bicyclic compounds, and we are going to use this some. But I think you can tell by the way that these bonds are drawn, where the directions are here, right? This is coming out toward us. That would be maybe a wedge. This is coming out toward us. That would be a wedge also, right? So either way, we don't need to draw those wedges with that structure there. In general, this is drawn without hashes and wedges. All right, so this is an introduction to 3D bond line structures. You've seen this in Principles of Chemistry or Gen Chemistry. These are the ones we're going to use most as hashes and wedges. I encourage you to use them frequently, and I also encourage you strongly to get your model set out and build these structures so that your eyes can begin to take on more information just by these hashes and wedges. All right, good luck.